Today we are going to discuss preloading and vertical drains. When highly compressible, normally consolidated clay soil layers lie at limited or large depth, large consolidation settlements are expected as the result of the loads from large buildings, highway embankments, or earth dams, etc. Pre-compression and provision of vertical drains in soft soil may be used to minimize post-construction settlement. This approach has resulted in a number of techniques involving pre-compression or preloading, sand drains, prefabricated vertical drains, vacuum consolidation, high vacuum densification method, HVDM. Embankment on clay foundation, and if you just look at the effect of surcharge treatment, when there is no surcharge, you can see with the passage of time the settlement is like this, and at this particular time you have got this much settlement. All right, but if we place surcharge, you could be able to get that much settlement in a shorter period of time. So that is the basic theme of that preloading. Well, same thing has been depicted over here. While you can see that when there is no surcharge, with the passage of time, you are having the settlement pattern like this, and you have got this much settlement after a longer period of time. But if we place this total surcharge, and then you can see what is happening. The rate of consolidation has been increased remarkably, and you can see that when you will remove this surcharge, you could be able to get the desired settlement in a relatively shorter span of time. The principle of pre-compression is explained in figure 1 shown below. So again you can see that when there is no surcharge, we are having the settlement pattern like this. But when this surcharge, the total surcharge, it has been placed, you can see the pattern is like this. And you can see that this much settlement you can get in this particular time, shorter span of time, T2. So here, if you just look at this one, this is the sigma dash P plus delta sigma dash F. This is the total surcharge which has been placed on the ground. And later we have removed that surcharge, and you are just having delta sigma dash P, this much. And this delta sigma dash P, this is the proposed structural load per unit area. The proposed structural load per unit area is delta sigma dash P, as I explained on the previous slide, and the thickness of clay layer undergoing consolidation is H sub C. The maximum primary consolidation settlement caused by the structural load is then can be determined by using this equation number 1. The settlement time relationship under the structural load is shown in figure 1b. However, if a surcharge of delta dash P plus delta dash F is placed on the ground, the primary consolidation settlement will be this much. So this is the formula for the primary consolidation settlement for this case. Now look at the sequence of steps in pre-compression or the preloading. The total settlement of S sub Cp will occur at time t2, which is much shorter than t1. Hence, if a temporary total surcharge of delta dash P plus delta sigma dash F is applied on the ground surface for time t2, the settlement will be equal to S sub Cp. At that time, if the surcharge is removed and a structure with a permanent load per unit area delta sigma dash P is built, and no appreciable settlement will occur then. So the total surcharge delta sigma dash P plus delta sigma dash F can be applied by means of temporary fill. So this is very important point, this one. Derivation of equation for obtaining delta sigma dash F and T2 from the figure 1b. Under a surcharge of delta sigma dash P plus delta sigma dash F, the degree of consolidation at time t2 after the application of load is this: S sub Cp over S sub C P plus F. So by substituting equation 1 and 2 in equation number 3, you can have this expression. Figure that you can see on this particular slide gives magnitude of degree of consolidation for various combination of delta sigma dash P over delta sigma naught and delta sigma dash F over delta sigma dash P. So you can see that there are vertical axis is meant for delta sigma dash F over delta sigma dash P. Horizontal axis is meant for the degree of consolidation, and you can see the number of curves, and these curves are for different values of delta sigma dash P over delta sigma dash naught. The degree of consolidation from equation 4 is actually the average degree of consolidation at time t2 as shown in figure 1b. But due to removal of surcharge and placement of structural load, the portion of clay close to the drainage surface will continue to swell, and the soil close to mid-plane will continue to settle. A conservative approach may solve this problem, that is, assume that U in equation 4 is the mid-plane degree of consolidation. So in this way you can see that this degree of consolidation is the factor of time. You can function of time factor. U is the function of time factor, this T sub V. So you can see here U means the mid-plane degree of consolidation, T sub V the time factor, and you know that is CVT2 over H square. CV, that is the coefficient of consolidation, T2 is the time, and H is the maximum drainage path. The variation of U and TV is given in figure 3. So this is the figure 3. You can see the variation of degree of consolidation with the time factor T sub V, you can see. Now here you would find one example. During construction of a highway bridge, the average permanent load on the clay layer is expected to increase by about 115 kN per square meter. The average effective overburden pressure at the middle of the clay layer is 210 kN per square meter. H sub C, that is 12 meter, C sub C is 0.81, E naught, that is 2.7, and CV, that is 1.08 meter square per month. The clay is normally consolidated. Determine part A, the total primary consolidation settlement of the bridge without pre-compression. Part B, the surcharge delta dash F needed to eliminate the entire primary consolidation settlement in 9 months by pre-compression. Now look at the solution. Part A. The primary consolidation settlement can be calculated by using this formula. So by plugging in the values, you can see you are getting 0.498 meter. That is obviously 498 millimeter. Part B. We know this formula for the time factor, and you can see the values of C sub V, H, as we are considering the two-way drainage, so it would become 12 divided by 2 that means 6 meter, and T2 that we are considering in this example, that is 9 months. So obviously the time factor is coming 0.27. So according to figure 3 that I have already shown, for T sub V 0.27, the value of degree of consolidation is 40%. We have delta sigma dash P, that is 115 kiloton per square meter, and the overburden pressure, that is delta that is sigma dash naught, that is 210 kiloton per square meter. So the ratio is obviously 0.548. So according to figure, for U is equal to 40% and delta sigma dash P over sigma naught dash, that is 0.548, you can get this one, delta sigma dash F over uh, delta sigma dash P, that is 2.5. And from here you can see that obviously this will be equal to 2.5 multiplied by sigma dash P, and you know delta sigma dash P, that is 115. So in this way we have got this much, delta sigma dash F. And keep this thing in the mind that when we are considering this one, that is the delta sigma dash F, this one, this is basically total surcharge minus proposed structural load per unit area. So I will repeat, this is the total surcharge minus proposed structural load per unit area, and that is coming this much. So assuming a bulk density of 20 kilonewton per cubic meter for fill material and a height of 5 meter gives a preload of 100 kilonewton per square meter. But look at this value is very large. The required surcharge is higher than the preload, and hence a consolidation by sand drains or prefabricated vertical drain is to be required. So the basically we have concluded this thing that in this case the fill height that is required corresponding to that is huge, and that's why simply preloading is not recommendable over here. We will have to consider the other options like sand drains and the option of prefabricated vertical drains with that. So when we place the surcharge over the ground, it is something like that. Look at that. A huge mass of soil has been placed over the ground. Now look at this particular slide here. You can see that we have just placed the preloading has been done, you can see, and we are not having any vertical drains in this part of the soil. But if we are having the vertical drains, that will improve the process of consolidation, and you could be able to get the desired results in a relatively shorter span of time. Now come to the topic of sand drains. The use of sand drains is another way to accelerate the consolidation settlement of soft, normally consolidated clay layers and achieve pre-compression before the construction of our desired foundation. Sand drains are constructed by drilling holes through the clay layers in the field at regular intervals. The holes are then backfilled with sand. This can be achieved by several means such as rotary drilling and then backfilling with sand, drilling by continuous flight auger with a hollow stem and backfilling with sand through the hollow stem, driving hollow steel piles. So there are different options in this regard which are available. The soil inside the pile is then jetted out after which backfilling with sand is done. Figure will show a schematic diagram of sand drain. After backfilling the drill holes with sand, a surcharge is applied at the ground surface. The surcharge will increase the pore water pressure in the clay. The excess pore water pressure in the clay will be dissipated by drainage, both vertically and radially. So basically when the sand drains are introduced, so you are having the drainage in the vertical direction as well as in the radial direction, thereby accelerating settlement of the clay layer. In figure, note that the radius of sand drain is R sub W. Figure on next slide shows the plan of the layout of the sand drains. The effective zone from which the radial drainage will be directed toward a given sand drain is approximately cylindrical with a diameter of d sub e. So here you can see this is the sand drain, this is another sand drain, and if you just look at the pattern of sand drains, so we are having that pattern of sand drains. So around one sand drain you are having the influence circle, and the diameter of that is d sub e. And if you just look at this one, that is the sand drain, so the radius of the sand drain that is r sub w. So here you can see that the vertical drainage is there and the drainage in the horizontal or radial direction is also present. So in this way, by introducing sand drains we can accelerate the process of consolidation. To increase degree of consolidation using sand drains or prefabricated vertical drains, we will discuss the prefabricated vertical drains. Average degree of consolidation due to drainage is UVR. So this is a new parameter, and that is equal to 1 minus into 1 minus U sub R into 1 minus U sub V, where U sub R, that is the average degree of consolidation with radial drainage only, U sub V, the average degree of consolidation with vertical drainage only. So this equation is very, very important. Okay, this slide is showing the schematic diagram of sand drain. So you can see that this is the sand drain, and you can see that the radius of sand drain, this is r sub w, and you can see that you are having the influence of that sand drain in approximately in a circular manner, and the diameter of that circle is d sub e. Now on this particular slide you can see one important thing, that is the smeared zone. If you just look at that, that is, this is the smeared zone. This one, this is also the smeared zone. So to understand that smeared zone, I need your attention. During the installation of sand drains, disturbance of the soil adjacent to the drain is likely to decrease its permeability and thus slow down the consolidation process. This effect is described as smear. So look at this one, this part and this part. So in this region you can say the soil is disturbed, and because of that, you are having the decrease in the permeability in this part. So that is called as the smeared zone. So if you just look at that, this radius is r sub s, and if you just look at this radius, this is r sub e. Now again, look at the smear. One thing that you must keep in the mind, that the size of the sand grain also has influence on the extent of the disturbed zone. Or you can say that this smear zone, this one, the smear effect increases with the increase in drain diameter. You can say this thing. And one more thing that you must keep in the mind for the smeared zone, it also depends on the method of installation. Dynamic driving creates more discordance of the soil than static pushing. So keep this thing in the mind, that during the installation of the sand drain, this is the sand drain, disturbance of the soil adjacent to the drain, here this one and this one, is likely to decrease its permeability and thus slow down the consolidation process. This effect is described as smear. Okay, when the surcharge is to be placed, there are two options. One option is that we can apply that total surcharge instantaneously, that means in a shorter span of time we can place. But if your soil is very soft, you cannot dump this much total surcharge instantaneously or in a shorter span of time. In that particular case, we will place that surcharge slowly. Let's say you have placed this much surcharge slowly in a period of 1 month. So this type of loading is called as ramp loading. So this loading is called as the ramp loading, and this is the instantaneous loading. So average degree of consolidation due to radial drainage, this is the formula, and here the formula is M written, and keep this thing in the mind that N is equal to D sub E over 2 RW, or you can say RE over RW. So in the coming slides, even you would find a number of formulas which are interrelated with each other. So you will have to go through these formulas with care. S is equal to R sub S over RW, and K sub H is the hydraulic conductivity of clay in the horizontal direction in the unsmeared zone. K sub R, the horizontal hydraulic conductivity in the smeared zone. So I showed the smeared zone in the previous slide, one of the previous slide. T sub R, the non-dimensional time factor for radial drainage only, and that is equal to this. So C sub VR, that is the coefficient of consolidation for radial drainage, and this is the formula for that. For a smear case is for a no smear case, that means disturbance is not there adjacent to the sand grain, then R sub S becomes equal to RW. So this is very, very important point. You must keep this in the mind. And in that case, KH becomes equal to K sub R. So S is equal to 1, and the equation 3 becomes like this. Sand drains enhance radial consolidation. The relevant equations which relate the degree of consolidation to spacing of drains for no smear case, that is for ramp loading, are as follows. Plots or tables can be prepared using the equation. So look at the formula for M, and then U sub R, and then in this formula A is equal to this and T sub RC is equal to this. So here you can see the variation of U sub V with T sub V and T sub C, and here if you just look at these different curves in the circle, we are having a time factor T sub C. For different T sub C we are having these curves, and here you can see that this is the time factor horizontally T sub V, and along vertical axis we are having the degree of consolidation U sub V. So U sub V, T sub V, and here these are the encircled values are T sub C values. And you know what is T sub C? This is the time factor corresponding to this time T sub C, where you have placed at that particular time you have placed the total surcharge. So corresponding to this time, whatever the time factor is there, that is T sub capital T sub C. Okay, now we have reached here, that is the prefabricated vertical drains. The prefabricated band drains are used for accelerating the construction for the accelerating the consolidation of marine deposits or soft clays, soft soils. In general, prefabricated band drains consist of a central core whose function is primarily to act as a free drainage channel and non-woven filter jacket, which prevents the soil surrounding the drain from entering the central core but allows water to flow in. So band drain is commonly used because of its easy prefabrication, easy quality control and economy, and small disturbance to the surrounding soil during installation. So you can see the prefabricated vertical drain. So this is a special material that is being used in the construction of prefabricated drains. So here if you just look at that, when there is no drain, the pattern of settlement is like this. Longer period of time is required for the settlement. Now look at this curve, the second one. This is the case where the drains are there but without surcharge. So you can see with the introduction of drain, there is improvement in the settlement pattern. You can get the desired settlement in a shorter span of time relatively. But when you are having the drains with surcharge, you can get the desired settlement in a very shorter span, very short time, So maximum benefit you are getting in this case, in which you are having the drains with surcharge. Equivalent drain radius of band-shaped vertical drain. The radius of sand drains or their derivatives such as sand wicks or plastic tube drains can easily be determined from the size of the mandrel, which is usually circular in cross section. Well, if you just read this particular point again, there are some important terms that we have used. Wick. Wick is basically, you can say, any piece of porous material that conveys liquid by capillary action. Then there is the word mandrel. Basically, steel mandrel is used, a tool or component of tool that guides or grips or clamps something is known as mandrel. So just to grip the prefabricated vertical drain, we are having that special tool that is called as mandrel. Okay, for prefabricated drains, however, the situation is different. The band shape of prefabricated drains, the flow pattern around the drain is considerably altered from the cylindrical case. Therefore, an equivalent drain radius ought to be calculated. So different uh, trade names are available for the prefabricated vertical drains, and in the core we are having different materials, and the filter types are also mentioned. So equivalent diameter of the prefabricated vertical drain can be determined by using this formula, and here B is the width of the strip and T is the thickness of that prefabricated vertical drain. Okay, drain design. Vertical drains and preloading are very effective and economical ground modification techniques for accelerating primary consolidation and compensating some secondary compression of soft compressible soils. The design of vertical consolidation using wick drains is based on theory developed by S. Hambo in 1979, which is used to calculate the spacing of the wick drains based on the horizontal coefficient of consolidation C sub h of the subsoil. The drains are normally installed in a triangular or square pattern. The rate of soil consolidation or settlement is controlled by how rapidly the pore water can escape from the soil. The controlling variables are the spacing between the wick drains and the permeability of the soil. By developing a set of design curves of drain spacing, fill height, and consolidation time, the most economical drain spacing and height of fill can be selected to achieve a given degree of consolidation in a specified time period. Vertical drain spacing. Vertical drains are generally installed in either triangular or square pattern. The consolidation problem is simplified to an axisymmetric one in most vertical drain consolidation theories, in which a drain well is enclosed by a cylinder of soil. An equivalent radius of the soil cylinder based on the same total area for different installation pattern is used in the analysis. So here you can see that this is the vertical drain which is being considered, and obviously we are having the influence of this vertical drain in a circular pattern, and this is the radius of that, of that influence circle. Here on this particular slide you can see the layout of square grid pattern. So you are having different drains. The radius of the drain is r sub d, and that is equal to r sub w, and you can see the influence circle, and this radius is r sub e. So again you can see over here in this case this is r sub e, and r sub d is the radius of effective radius of that drain, and this d is the center to center spacing. Here the center to center spacing is this one. Trial embankments. These are useful to determine the feasibility of preloading and vertical drains in the field and avoids uncertainties in sampling, field properties, and installations. It needs to reproduce stress and field conditions that are representation of actual structure. It should be part of final structure. It needs to be instrumented using piezometers, settlement gauges, leveling points, etc. So instrumentation of vertical drains. So you can see that different we are having instrumentation. You can see here we are having the piezometers which are to be installed just to determine the pressures. So in this way, you will have to install the piezometers at different levels. You can see here, look at that. Vertical drain installation sequence. Position rig at drain location. Place anchor on drain end. Penetrate mandrel to desired depth. Withdraw mandrel. Cut drain mandrel above drainage blanket. So this is a wick drain or the band drain. A closer view of that prefabricated vertical drain that will be installed into the ground. And here you can see that this machine is being used, and here we have placed the band drain, and with the help of that mandrel, that drain is being installed. So we have gone up to the desired depth, and then it will be cut at the top. And in this way, we are having this drain, exposed part of the drain. So in this way, we can have a number of prefabricated vertical drain in this way, and then those can be connected horizontally with these special horizontal drains. So vertical drain, installation of drains on a barge. So even we can have a ship or special boat, and we can install the vertical drains, prefabricated vertical drain, by using that special arrangement. Potential advantage of vertical drains. The advantage of vertical drains are threefold. Number one, increased rate of gain of shear strength of clay. That means enable the load to be applied more rapidly, thus better use of construction plant, lower amount of fill required, increased rate of consolidation, consequent savings in construction cost. Second, increased rate of consolidation, that means reduction in time required for primary settlement. Structure or embankment can put into commission and use for far earlier. Reduction in cost of maintenance. And the third aspect is the stability to embankments. Many soft clay strata contain thin band or parting of sand or silt. Excess horizontal spread of pore pressure along these partings take place. Vertical drains installed can relieve these excess pore pressure. Now the application of prefabricated vertical drain. PVD stands for prefabricated vertical drain. Airport runways, golf courses, dredge consolidation, mine tailing consolidation, tailing ponds, swampland, wetland development, building foundations, retaining walls, parking lots, landfills. Okay, here you can see the word dredge. Dredge is basically very fine mineral matter held in suspension in water. Okay, now the installation. Installation of vertical drains. Drains shall be installed with approved modern equipment of a type which will cause a minimum of disturbance of the subsoil during the installation operation. The first step in the installation is to prepare a working surface for the installation rig. The working surface must be level and have enough bearing capacity so that the installation rig can operate. Typically, this working surface is also part of the gravel drainage layer. After the site is stripped, a geogrid is often placed for support and then the drainage or working layer placed. Once the working layer is in place, the installation unit starts work. Layfield's new bottom-mount hydraulic wick drain rig is mounted on an excavator. It presses a steel mandrel into the ground up to 120 feet deep. The PVDs are placed in a pattern as specified by the project engineer. Typically, it is a triangular pattern 2 meter on center. In some cases, there will be a cap of hard soil on top of the soft subsoil. In these cases, pre-drilling may be required. A suitable drill will operate ahead of the PVD installation rig to prepare holes through the hard upper layer. Once the wick drain PVDs are placed on a drainage layer is placed on the top to prevent PVDs. So this point must be noted that once the wick drain are placed as a drainage layer is placed on the top to prevent PVDs. This drainage layer is typically a free draining gravel or a drainage geosynthetic. The drainage layer needs to be sloped so that the water will flow away from the foundation. The slope needs to take into account any planned settlement so that water flow is maintained throughout the consolidation phase of the project. Now, the installation method of vertical drains. So we are having the different groups like displacement method, where we are having driving, vibration, pull down, static force, washing combination of above, the displacement method. Then drilling methods, rotary drill with or without a casing, rotary auger including continuous standard and hollow flight augers, percussive shell and auger method with or without casing, hand auger. And then comes the washing methods where the rotary wash jet washed open-ended case, weighted wash jet head on flexible hose. Now this topic is also very important, that is the advantages of PVDs over sand drains. We have discussed the sand drains and the PVDs. The installation rate of PVDs is typically 5,000 linear meter per day, which results in a significantly lower project cost. This is a very good point. There is no risk of PVDs breaking installation, while sand drains may have discontinuities if the mandrel is withdrawn too fast. There is no risk of shear failure of PVDs during settlement, while sand drains are vulnerable to shear failure during settlement. PVDs have discharge capacities typically 30 into 10 raised to the minus 6 to 90 into 10 raised to the minus 6 cubic meter per second, while a 0.35 meter diameter sand drain has a discharge capacity of about 20 to 10 raised to the minus 6 cubic meter per second. When installed with a properly designed mandrel, smear effects are much less for PVDs than for large diameter sand drains. The zone of smear is directly proportional to the diameter of mandrel used for installation. PVDs are factory produced material and are quality controlled, whereas sand drains are subject to quality variance of naturally occurring sands. Now the slide for conclusions. Preload enables consolidation of soil in vertical direction only. And hence sand drains in addition to preloading are used to accelerate the consolidation of soils. This results in reduction or lesser preload. It facilitates radial consolidation in addition to vertical consolidation, significantly increasing the consolidation rates. Sand drains have been used since 1930s, and prefabricated vertical drains in the form of cardboard wicks were used initially. Now prefabricated vertical drains are being used all over the world. In addition, vacuum consolidation that we'll discuss in the next class, along with preloading and PVDs, is done to increase the efficiency of the whole process. Now, at the end of this lecture, you would find some solved examples. Example 1 we have already discussed, that is the same problem. Now look at this example 2. Redo example 1 with the addition of some sand drains. Assume that R sub W is 0.1 meter, D is equal to 3 meter, CV is equal to C sub VR, and the surcharge is applied instantaneously. So instantaneously surcharge has been applied. So we are not having the ramp loading in this case. Also assume that this is a no smear case. So in this example you would find the various you can say the formulas used that we have already discussed. So the problem has been solved step by step, so you will have to go through this problem. So the solution is given, so you will have to go through the solution of this problem with care. And then you can see that here I have accommodated the tables, because graphs are available, tables are also available, and here you can see that this table is showing the variation of u sub r for various values of t sub r and n. So here you can see the n values, different n values are given, and you know n is equal to re divided by rw. So either you can use the charts, you can use the graphs, or you can use such type of tables which are available. Then you would find the example 3, that calculate degree of consolidation at different times after the installation. So the information is given, data, and again you would find that in this question the ramp loading has been considered, and the ramp loading, it has been applied over a period of 60 days. So look at that, 60 days period, that means of 2 months. So you will have to go through this problem. So you would find the application of different formulas that we have already discussed. So simply the application of the formulas, and you know at the end we have got the settlement after 30 days, that is 54.36 millimeter. So you will have to go through all these solved examples. The solution is provided step by step, so you will not be facing any problem. So that's all about the preloading and the vertical drains.